Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to the nanoHUB-U course, Thermal Energy at the Nanoscale. I'm Tim Fisher, and we're in the middle of week 5. Today we're going to talk about Phonon-Phonon scattering. I'm going to start out with a little bit of a physical explanation. So imagine if we had a field of, or an array of atoms that were connected by harmonic springs, so perfect springs. As waves moved through this medium, as they encountered, let's say, an atom at some position in the array, if that atom were somehow off of its equilibrium position, let's say it was moving because of a different carrier, a different phonon that was moving through, then it would still have the same curvature. If it stayed on the harmonic curve, it would have the same curvature as it does at the base. So let's say it was out here, and so it would essentially have the same spring constant. It would feel like the same spring constant, and it would not be scattered. There would be no interaction because, again, all of these harmonic waves are lossless, and so the waves would just kind of travel through each other. However, if the atom were instead, if there were some anharmonicity, let's say it's out at this point here, and that's how it is in the real world, then it would have a different spring constant than it does when it's at its equilibrium position, which is sort of the place about which we perturb to find an approximate harmonic potential. And so now with this different spring constant, that will change the way that it interacts with the rest of the lattice, and in fact then phonons can scatter. And so this strain causes a difference in stiffness or spring constant, and this type of scattering is sometimes called intrinsic scattering because it can happen and does happen in pure crystals. So even if we have a perfect crystal, we will have scattering of phonons by themselves or with each other, and that will produce a finite thermal conductivity or a non-ballistic type of thermal conductivity. And it's a very complicated subject in general. We're going to go through a couple of the more simple types. We're only going to talk, in fact, about 3 phonon scattering processes. As you might imagine, you could have many more than those, but many more phonons interacting together, although with lower probability. So the 3 phonon interactions, what we're doing when we count phonons in terms of 3 or 4 or 5 phonons, what we're saying is that we have, say, 2 incoming phonons that produce 1 outgoing phonon. That's shown in the first example. That's A on this slide. Or a phonon that's moving through a crystal can just decompose into 2 other phonons. So that's identified here as type B. And those 2 types, A and B, the way that we've drawn them, are what we call normal processes because the momentum conservation statement holds. That's K1 plus K2 equals K3 for type A, and K1 equals K2 plus K3 for type B. And in all cases, the frequencies add and balance each other because that's a statement of energy conservation. It's the bottom one that is a bit strange and surprising often to students. What we have down here is called a U process, or Umklapp. That's a German word for reversing itself. And now the way I've drawn it here is we have 2 phonons going in, K1 and K2, and they would normally produce a wave vector that's shown in the dashed line here. But for some reason, that wave vector is forbidden. I'll talk about the reasons for that in a moment. But because that wave vector is forbidden, it has to be translated back to an allowable wave vector, and we use the reciprocal lattice vector G, if you remember that from long ago, to do that translation back into into an allowable wave vector. In this case, that would be K3. Well, you'll notice something about this. K1 and K2 had a substantial amount of momentum going from left to right here, but K3 is going from right to left. So somehow this process has reversed the momentum of these two carriers, and that produces an impedance or resistance to heat flow. Let's look a little bit, we'll look at a specific example. Our favorite example in this course is graphene. So here we have the first Brillouin zone of graphene, and I'll talk initially about the scattering that we see on the left side. So K1 plus K2 equals K3. This is all good. Everything is allowable, at least the way we've drawn it. And the reason that we say that's allowable is because the final wave vector, that's K3, is sitting at least at a legitimate position. There's some more things we would need to do to make sure that was right, and we'll talk about those, especially with respect to energy conservation. But we'll assume that one is fine for now. However, on the right side, we have K1 plus K2. There's K2. And that would produce a wave vector that's this red line. I'm circling the arrowhead. And that wave vector would put us outside the first Brillouin zone. What does that mean? Well, of course, reciprocal space goes on and on. And so, certainly reciprocal space does exist there. But if we remember back to what reciprocal space means, there's an edge to the reciprocal space because the wave vector, very large wave vectors imply very small wavelengths. And so the lattice cannot support wavelengths that are that small, even though the reciprocal space is symmetric with itself. And so what we have to do is to translate that back by a reciprocal lattice vector. In this case, we've chosen this reciprocal lattice vector G, which connects the gamma point to the top right unit cell's gamma point. So we now, we have to find a wave vector K3, which when we add the reciprocal lattice vector G to it, that would put us at the position of K1 plus K2 in K space. You'll notice that just as in the last slide, now we have K1 and K2 have a sizable amount of momentum moving from left to right. K3, on the other hand, has very little momentum moving from left to right. And so we've lost some momentum along the way, and that's going to impede heat flow. So these consequences are stated here. The end processes, because they conserve momentum, they do not impede heat flow directly, but they do play an important role. And I'll go through a few slides. It's a even more complicated subject than just kind of understanding the basic scattering mechanisms themselves. But they are important to include in our analysis or in a very rigorous analysis because they redistribute the energy within the modes, the phonon modes that are allowable, and they can enhance the subsequent types of scattering events, and particularly U processes. On the other hand, U processes can and do impede phonon momentum, and these are what actually dominate. U processes dominate the thermal conductivity behavior of bulk semiconductors and insulators, at least if they're highly pure materials, crystals. All right, I mentioned before that we have to conserve energy, and so it's not like we can just start drawing wave vectors around in the K-space map and say, well, that's a scattering event. It's legitimate because it's inside of the first Brillouin zone. In fact, we have to make sure that we conserve energy, and this is a really, really difficult part of the scattering analysis. And so we're going to use graphene as an example. In this case, what we have is a surface I'm showing on the left from some work that we've done in my group. That's a surface of energy imbalance, and what we need to find, or we need to highlight the places where the energy imbalance is zero. So where this three-dimensional curve intersects the delta W equals 0 plane, those are the only ones that are allowed, only scattering events that would be allowed, because anything else would not conserve energy. And in this case, it's for two ZA modes turning into a TA mode for graphene. This is what a map looks like for several different types of scattering events, and you can see that we're coupling longitudinal and Z. That's the flexural modes for graphene phonon branches, and we see that. And in this case we've fixed K1 and just looked at what are the allowable types of allowable wave vectors for type 2 and type 1. These type 1 and type 2 have to do with the whether they're one phonon turning into two or two phonons colliding and turning into one. But you can see that this map is, there's no easy functional forms that you could at least imagine for these for mapping this energy space, and so it is quite challenging to do all of the statistics. What you end up having to do is to discretize K-space, the first Brillouin zone, into small segments and just look at all of the possibilities for scattering from one branch to another, and then go through all of the possible permutations, including the permutations of the magnitudes of the wave vectors. So it's very computationally intensive. So the way to simplify that a bit, or the way to do this in a more practical engineering type of approach, is to use some engineering models for it. Now, the full version of scattering is basically you take Schrodinger's equation, quantum mechanics, you apply some perturbation theory to it, and then look at all of the different possible scattering types. And you use something called Fermi's golden rule, which is really a way to make sure that you're accounting for all the different possibilities properly, to guide all of the different types of scattering events, and those turn into a huge matrix of scattering, of coupling factors, interaction matrix they call it sometimes. Engineering models are generally simpler. I guess that's maybe redundant to say it like that, but the engineering models typically use a power law form. So if I were interested in the phonon-phonon scattering rate, that's tau to the -1 power. Generally, you'll find that the models look like a constant multiplying the frequency to some power n multiplied by temperature to some power m, and usually n and m are integers. There's not always a good physical reason why they need to be, but they're often in engineering models used as such. So looking at some of the more popular models, end process scattering events generally, again, have this power law form. And longitudinal modes and branches tend to have different models than transverse. And for low and high temperatures, you see that there's a distinction between the temperature regimes, and usually that's the physical reason for that is that you have a different you have a different occupation. So there's a different level of occupation of phonons at different temperatures. There is no, for U process scattering, there are many proposed models. There's not anything that I would consider to be universal. One of the ones that's very popular for three-dimensional bulk materials is the model by Clemens. There's actually a moderate to low temperature version. That's the one that's shown here in this first equation. And then there's a high temperature extension. And you can see that now we have different polarizations that have their certain engineering models for scattering. And then different temperature ranges have different, even for the same type of scattering event, the same branch, a change in temperature range will produce a different model. So really what one has to do this completely and rigorously is to quilt all of these engineering models together, depending on what types of phonons you're interested in. Usually it's all of them, and you kind of combine all the scattering events together. And then the temperature ranges that you're interested in. But one way to kind of pull everything together, again, this is an engineering approximation, is to assume that the scattering processes are independent, meaning that the existence of one type of scattering event does not promote or impede another type locally. And if that's true, if the scattering is indeed independent, then what we can do is just add the scattering rates together. And this is called Matheson's rule. So tau to the -1, this is an effective scattering rate. Often you'll see it written with the subscript EFF. And that'll just be the sum of the different scattering processes that are relevant. And so this is where we actually, it's not just phonon-phonon processes, but we add boundary scattering and impurity scattering to this. And we come up with, it at the end, an effective scattering rate that we can put into a model such as the Landauer model that we talked about, or the kinetic model. I will say the last bullet here is important. Often we don't really know what the best model is. We don't know which types of scattering are dominant. Maybe we don't know enough about the material. Maybe we don't know about the roughness, the surface roughness of the boundaries, or the interfaces, or the grain boundaries. And so what we do is we make experimental measurements and then extract an effective scattering rate from that based on a property that we measure, in this case, thermal conductivity. I want to say one thing about, about these end processes. So if we had this, we go ahead and plug in our scattering rate, in this case it's scattering time, into our kinetic result that's shown in the top equation. If we did that blindly and put n processes, lumped n processes in with u processes and any others that we had, then that would affect the effective scattering rate. And that would not be correct, because then it would imply that n processes do contribute to thermal resistance when in fact they do not. And so I just wanted to point this out and to say a few more words about it. N processes modeling has to be done because, as you might expect, U processes happen typically with very large wave vectors. So we have wave vectors that are out toward the edge of the Brillouin zone, and when that happens, then if we have a phonon that's out toward the edge of the Brillouin zone, it's much more likely to scatter with another phonon that would put it outside the boundary of the Brillouin zone, thus producing a U process. So N processes can actually build up those large wave vectors that then turn into U processes later. And that's why the way I put it on this slide is that N processes can feed U processes. So that's why it's often important to keep them there. So with this, looking at all of kind of pulling together the phonon scattering concepts that we've studied, we've had defect and boundary scattering. We used a subscript I for that. For defect scattering, impurity scattering, sometimes it's called. That's why the I is there. Boundary scattering has a subscript B. Umklapp scattering is here. And Umklapp scattering needs to be informed typically by your sub-model for N processes. Once we've done all these things, then we can calculate an effective relaxation time, tau, or an effective relaxation rate. And I remind you again that Matheson's rule presumes that there are no interactions among these scattering events, at least the ones that lead to resistance to heat flow. And we've kind of used scattering rate, scattering time, tau, and mean free path interchangeably. If you're more comfortable with mean free path, that's what we've used more in the previous lectures. It's just the product of the scattering time, tau, and the group velocity, Vg. All right. Lastly, I wanted to point out how this ends up looking for thermal conductivity. So I've taken a nice graph from Professor Caviani's book, where he shows different domains of contributions to thermal conductivity. So once again, we have, just to remind ourselves, we have the expression for thermal conductivity in the equation on the top right. At very low temperatures, what we'll find is that U processes are essentially frozen out. So the things that we're interested in there would be the boundary scattering, impurity scattering. Those are the two that will be dominant there. And then, as we have very low temperatures, the specific heat is changing rapidly. That's in this region here. And so we see a pronounced increase in thermal conductivity, and it's mainly because the scattering rates tend to be roughly constant, not always, but roughly constant down there. But the specific heat is increasing rapidly. Then the specific heat, as we recall from the law of Dulong and Petit, levels out. And at the same time, for most materials, then you start to see the U processes kick in. These U processes then will tend to, again, increase. The scattering rates increase as frequency increases. And so they'll become more and more dominant. And then you'll start to see, with a constant specific heat and a decreasing scattering time, you'll start to see thermal conductivity drop. And that's what this part of the curve says. So with that, I'll leave you, and we'll talk some more next time. Thanks.